Hello everyone. In this lecture we will discuss about the mass transfer in the reacting system. This lecture is related to mass transfer and reaction engineering. So what are the mass transfer behind the chemical reaction engineering? How mass are transferring in the chemical reactions? So the first step this is the first topic of this chapter, mass transfer in reacting system, in the book of Elements of Chemical Reaction Engineering by Fowler. So molar flux balances in Cartesian coordinate system. Molar flux balances in Cartesian coordinate system. Molar flux balances in Cartesian coordinate system. So first of all we should know mole balances. We should know the mole balances, molar flux balances. So in the previous chapters we have already discussed that the molar flow rate of component A is denoted by Fa, and the molar flow rate of component A is related to the concentration of component A by Fa is equal to Ca and to the volumetric flow rate of component A. So the molar flow rate of component A is equal to concentration of component A and to the volumetric flow rate of component A. We also know from the Fick's law that molar flux of component, molar or molecular molar flux of component A is denoted by the Na, or we can also denote it by Wa. So Wa is the molar flux of component A, and molar flux is nothing but mole of component A passing through area A and time T, and this mole per unit time is nothing but it is the molar rate of component A, and molar rate of component A is nothing but this one. This is the molar rate. So this is the mole per unit time and to the area, and the mole per unit time is molar rate. So it is the Fa of component A, and this is the area through which component A is transferring. So this is the area. So this is equal to Wa. This is W. This is Wa. So we can also denote the molar rate of component A is equal to molar flux of component A and multiply by the area through which the component A is transferring. So this is the relationship between molar flux and the molar flow rate. So now the molar flux in Cartesian coordinate system, molar flux balances. So the molar flux balances, balances equation will derive from the material balance equation. So first of all we should know the Cartesian coordinate system, a rectangular Cartesian coordinate system. What is the rectangular Cartesian coordinate system? It is, you have already discussed that in the higher class mathematics. This is the Cartesian coordinate system, rectangular Cartesian coordinate system. So this is the coordinate system. This is the x-axis. Suppose this is x-axis, this is y-axis, and this is the z-axis. This is the z-axis also, and this is the x, y, and z, and the whole is our control volume. So we will derive equation with the help of this Cartesian coordinate system. So this is a three-dimensional figure. Now we will derive the molar flux balances equation in Cartesian coordinate system. So our Cartesian coordinate system is, this is our Cartesian coordinate system. So Cartesian coordinate system. So this is the Cartesian coordinate system. This yes. This is the Cartesian coordinate system. Now suppose this one is the, I am giving it a proper color to identify the xy and z direction. So suppose this is the x-axis, and this is the y-axis, and this is the y-axis, and the z-axis, this is the z-axis, Oh, now the molar rate of component A will pass through this side. It will enter through this. It can enter through this side, and it can leave through this side. Similarly, the molar flow rate of component A can enter through this side, and it can leave through this side. Similarly, the molar flow rate of component A can enter through this side, through this z direction, and it can leave through z direction. So the molar rate of component A, enter to the system at this position, at this x position. Suppose this is the x-axis. You can see this is x, and this one is x plus delta x. So the molar flow rate of component A entering to the system at x position is Fa. Molar flow rate of component A enter to the system. This whole is a system. So at x is this one, and the molar flow rate of component A leaving the system at x plus delta x is denoted by Fa, x plus delta x. Similarly, the molar flow rate of component A can enter the system through y direction. This is the y direction. So it will be denoted by Fa y, and the molar flow rate of component A leaving the system at y plus delta y direction will be denoted by Fa y plus delta y. This position is y plus delta y, this side y plus delta y, and this is the y, Similarly, this is the z, and this side is the z plus delta z. So the molar flow rate of component A entering through z direction is Fa at z position, and leaving it, suppose I am writing it here in this place, Fa z plus delta z, and this delta x, this is the delta x, this one is the delta y, and this one is the delta z. This is the delta z, this is the delta x, and this is the delta y, and delta x, delta y, delta z is nothing but volume of this cube, volume of this system, or this cube, this Cartesian coordinate system. So this is the volume, because this is the three sides, length multiply by length multiply by length, nothing but volume. Now I am writing the material balance equation to derive the molar flux balances in the rectangular coordinate system. So the material balance equation is nothing but it is input minus output, plus generation minus consumption is equal to accumulation. So the component A can enter through x direction, it can enter through y direction, it is entering through z direction. So component A is entering from x direction, it can enter from y direction, it is also entering from z direction. So component A is entering from x, y and z direction to the system. and the component A is living at x plus delta x position. Similarly, the component A can leave the system at y plus delta y position, and the component A is also leaving the system at z plus delta z position. So the entering the molar flow rate of component A entering to the system at x position is Fa x position. The molar flow rate of component A entering to the system at y position is Fa at y. The molar flow rate of component A enter the system at z position is Fa z. Similarly, the molar flow rate of component A leaving the system at x plus delta x, this is the entering term, this is the now entering input minus output. So component A leave the system at x plus delta x position, Fa x plus delta x, and it is leaving the system at y plus delta y position, and it is leaving the system at z plus delta z position. This is the output term. Plus generation, so the rate of generation is of component A is Ra, but the unit of mole is molar flow rate is mole per unit time. So the unit of this one is mole per unit time m2 volume. So the molar rate or the rate of generation of component A inside the system, or the rate of consumption of component A inside the system, is denoted by Ra. So suppose A is generating inside the system, Ra can consume, so I am writing it plus Ra, and to the volume of the system, so the volume of the system is delta x, delta y, and delta z, because this is the volume, and the unit of Ra is mole per unit volume and 2 times. So this volume will be cancelled with this whole volume, and it will be mole per unit time, which is the unit of these terms. So, and suppose the consumption is 0, A is not consuming, but A is accumulating, A is changing inside the system. So A is changing, so I am writing it change in the concentration of component A with the passage of time in the Cartesian coordinate system, or in the volume, with the passage of time in the volume, in delta x, delta y, and delta z volume, this volume. So this is the material balance equation to obtain the molar flux balance. So now we know that the molar flux of component A is also written, can be also written as Wa molar flux, and to the area, this is the area through which the component is flowing. So the this is the relationship between molar flow rate and molar flux. So suppose if A is entering to the system at x position, then what will be its relation with molar flux? So it will be Wa, and to the area through which A is flowing. So the area will be delta y, delta z. So you can also write it, you can see it, Fa. So this is the x position, this was the x position, Fa. So Fa at x position, so the area will be this area, A is passing through this area and this area, the perpendicular area. So the perpendicular area is z, this area is z direction, and this is the y direction, so z and y. Similarly for y, it will be this area, perpendicular area. So the perpendicular area is this xo, and this one x and z. Similarly for z, it will be this area. This is the x-axis and y. So you will write this one. So apex can be written as this, can be written in this way. So I am writing it WA delta y delta z, and this is the at x position, plus WA, and for y this is the, for y this will be the x and z. If this is y, this definitely the area will be x and z. If this is x, the area will be, the perpendicular area will be y and z. If this is z, if this is z, then the perpendicular area will be x and y. So this is the y, so it will be the x and z. Point number y, and this will be the WA, and the z, for z position it will be the x and y, and this is the z. So these are the entering term, these are the entering term. Now the leaving term, so WA, x, y and z at point x plus delta x, the WA, x and z at point y plus delta y, and WA, x and y at point z plus delta z. So this is the entering minus leaving, this is the leaving, this is the leaving, this is comma, this is the leaving, z plus delta z. Input minus output, and the generation is RA delta x delta y delta z, and the accumulation is change in concentration with the passage of time, and delta x delta y and delta z. Now suppose this is equation number A. Divide this equation A by volume by delta x delta y and delta z. So divide this equation by volume, delta x delta y and delta z. So this will be delta x delta y delta z. These will cancel with this one, this will be cancelled with delta x delta y delta z, this will cancel with this one. So this whole term will be divided by delta x delta y delta z, and this whole term will also divided by delta x delta y delta z. In these term you can see that this is the, if it is denoted divided by delta x delta y delta z, then this delta y delta z will cancel with this delta delta y delta z, and delta x will come in the denominator of this term. Similarly delta x will come in the denominator of this term, and if you divide by delta x delta y delta z, then x and z will cancel, x and z will cancel with this x and z, and delta y will come to the denominator of this one, and delta y will also come to the denominator of this delta y plus delta y term, and the x and z similarly when divided by x, y and z, then x and y cancel with x and y, and this will be the delta z term. So after simplification, this was WA y and z, and this was at x position input plus so I am writing at x position and minus x plus delta x position. So WA y z at x plus delta x position. Similarly for y, this will be the WA for y position, it will be the x and z at point y minus WA x z at y plus delta y. Similarly, WA flux, and this is the z direction, so it will be x and y at z position minus WA x and y at point z plus delta z, and this was RA and the volume x, y and z, and this is the change in concentration of A with the passage of time x, y, z. So divide this whole term by, I am repeating it here in this place. Divide the whole equation. Suppose this is equation number A. This whole equation is equation number A. Suppose this whole equation is equation number A. So divide this equation by delta x, delta y, delta z. So each and every term will be divided by delta x, delta y, and delta z. So this term will cancel, this whole term will cancel with this delta x, delta y, delta z will cancel with this term, and here the delta x, delta y, and delta z, and this term will also divided by delta x, delta y, delta z, and this term will also divided by delta x, delta y, delta z. So the delta y and delta z will cancel with this one, and then the denominator only this delta x will come. The xz term will cancel with xz, and here only delta y will come. The x and y term will cancel with this one, and here only delta z will come. So delta y, final equation will be WA at x minus WA x plus delta x divided by delta x plus WA at point y minus WA at point y plus delta y, and divided by this delta y plus WA at point z minus WA at point z plus delta z, and divided by this delta z, this one delta z. Now this is the definition of the first order derivative. This is also the definition of first order derivative. This is also, so, and this is plus RA is equal to dCA by dt, because these are cancelled with each other. So RA. Now from the definition of first order derivative, if delta x, delta y, delta x tends to 0, then this will be equal to delta x. If delta y tends to 0, then this will become delta y, and delta z tend to 0, then we will write this delta z in this form. So using the definition of first order derivative, we will write this equation. Suppose this is equation number, this whole is equation number, suppose this is equation number 2. So the after simplification and using the definition of first order derivative, the equation number 2 will be written as minus dWA by dx minus dWA by dy minus dWA by dz plus RA is equal to dCA by dt. So this is the flux which are changes in the x, y, and z direction in the Cartesian coordinate system, and reaction is also taking place in the Cartesian coordinate system, and this equation is called the molar flux balance equation in the Cartesian coordinate system. So this is the molar flux balance equation in the Cartesian coordinate system. Now it will depend on the problem. Sometime it is given to us that the molar flux is not changes in the y direction, so we will ignore, sometime we can ignore this term, we can ignore this term, so we can simplify this equation. So this is the molar flux balance equation, molar flux balance equation in Cartesian coordinate system. So this was all about the molar flux balances in the Cartesian coordinate system, and was the first topic of the mass transfer and in reacting system. So the combination of mass transfer and reaction engineering. So in the coming lecture we will discuss the other topics related to the um, mass transfer and reaction engineering. Thank you very much for your attention. If you are new, you can also subscribe, like the YouTube. Thank you very much for your attention.